Hi students, in this video we are going to see a problem based on continuous time Fourier series. So problem is this: obtain a Fourier series for the following waveform. So waveform is given like this. Basically a triangular waveform is given. So on and so forth. So this is a waveform given. For this we need to obtain a Fourier series. Now the thumb rule is that we need to find out the time period, and time period is nothing but time taken by a waveform to complete one cycle. So over here also we need to find out what is a cycle. While taking a cycle, you can start from any point and come back to the waveform which is a repeating part of itself. Meaning, instead of starting from 0 to 2, because I know this is the waveform which is repeating, I will take cycle between these two intervals. So this particular part of the waveform will become a cycle for me. So the time between these two is a time period, because that is completing one cycle in this span. So see, this part is repeating itself. So you can start -1 and you can end at 1 to complete a cycle. Why we have taken this? Because now next step is that during the interval which you have defined, you need to write an equation of this straight line. What I feel, writing an equation for these two is a bit easier compared to writing an equation for this. So we need to write an equation for these two. So time period I have decided from here to here, which is nothing but one minus -1, which is equal to 2. So fundamental time period is T is nothing but 2. So that fundamental frequency omega is 2 pi by T. So now I can say omega T is 2 pi, which implies 2 omega as 2 pi, or in other words I can say omega is nothing but pi. Next step is defining the equation. For that I will take the cycle aside. So this is a cycle that I have selected. Basically it's a combination of two straight lines. So let's write an equation of a straight line in 2-point form. This is having the coordinates -1, 1. This is origin 0, 0, and this point is having a coordinates 1, 1. So let's write an equation for this. So equation is y minus y1 upon y1 minus y2 equal to x minus x1 upon x1 minus x2. Whereas for this also we are having a same equation. So let's write the equation of this part of a line. So for this part the equation will be like this. I'm writing for this part. from -1 to 0. Y is nothing but this x of t. So x of t, y1 is nothing but 1. 1 minus y2 is 0. Equal to x is nothing but t. Minus x1 is minus 1. x1 and x2 is 0. So if I simplify, I will get x of t equal to, if I solve, I will get here minus x of t So I will get minus x of t plus 1 equal to t plus 1. So what exactly I have done? I have simplified this and cross multiply. So after solving this, we'll come to know this 1 get cancelled, and in the end x of t I will get as minus t. Later on we will write this properly. Now let's find out the equation for this in the similar manner. So I'll write here from 0 to 1. It is y minus y1 upon y1 minus y2 equal to x minus x1 upon x1 minus x2. So once again, doing a cross multiply, I will get minus x of t equal to minus t, which implies x of t has to be equal to t. So now I am getting very simple equations. So let's club these two equations together and we'll get a complete x of t minus t for the interval minus 1 to 0, and this should be equal to t for the interval 0 to 1. So this is our x of t defined from minus 1 to 1 with a time period equal to 2. This Fourier series representation for x of t can be given like this. X of t equals a0 plus summation n from 1 to infinity in bracket an cos n omega t plus bn sin n omega t. So let's find out a0, an and bn now. So a0 is given by 1 upon time period, and over here it exists from minus 1 to 1 x of t dt, and we know time period is 2, so straight away I can substitute t equal to 2. So this is nothing but 1 by 2. But the problem with x of t is that from minus 1 to 0 it is minus t, and from 0 to 1 it is t. So let's solve this. So a0 I will get 1 by 2 in bracket minus I have taken common, and integration of t is t square by 2. Limits are minus 1 to 0 plus, once again it's t square by 2. Limits this time from 0 to 1. So if I apply, I will get 1 by 2 minus 0 if I apply, so it's a 0 minus minus 1 square, it's 1, so it's 1 by 2 over here 1 by 2 minus 0. So after simplifying, I will get 1 by 2 in bracket 1 by 2 plus 1 by 2. 1 by 2, 1 by 2 is 1. So in the end, A0 we obtain as 1 by 2. So this is a DC or a constant term in the Fourier series of x of t. Let's find out an. An is 1 upon half the time period. Waveform exists from minus 1 to 1 x of t into cos n omega t dt. Since we know this t is 2, so 2 by 2 is 1. So in the end, an will be 1 upon 1. No need to write x of t minus 1 to 0. We have x of t as minus t. And from 0 to 1, it is plus t. So let's solve it. So for this, I take a minus common, and t cos nt, u into v formula of integration we need to apply. So I'm applying it directly. So it will be like this. A first term will be as it is, multiplied by integration of a second term. So over here, we consider this term as u and this term as v. So that first term will be as it is, repeat, integration of this will be sine n omega t upon n omega minus, we have to keep differentiating u till we are getting a 0. So differentiation of t will be 1 and integration of this term will be minus cos n omega t upon n square omega square. Further we can stop because derivative of 1 is 0. So henceforth all the terms will be 0. So this much of we have to do with the limits minus 1 to 0. Plus same technique we have to use for this integral, which will give us t sine n omega t upon n omega minus 1 in bracket minus cos n omega t upon n square omega square, and limits are 0 to 1. So let's first adjust this minus terms so that we can avoid a confusion. So if I adjust the minus term, I will get an as in bracket minus t into sine n omega t upon n omega. Over here, this minus, we are having 3 times minus. So in the end, result will be minus only. So it will be minus cos n omega t upon n square omega square. So to this, we have to apply the limit minus 1 to 0. Similarly over here, plus sign is there, minus will become plus. So in the end, I can do this as a plus in bracket t sine n omega t divided by n omega plus cos n omega t upon n square omega square. Limits are 0 to 1. Let's apply the limits now. So an you will get If I apply 0 over here, 0 getting multiplied with this sign, in the end result will be 0. 0 over here, if I put t is 0, it is a cos 0. So minus cos 0 upon n square omega square as the first limit, minus lower limit. If I apply over here, already minus is there, with one more minus 1 it will become a plus 1, and here it is sine minus n omega upon n omega we will get. This will be in one bracket. Rest, here also I need to apply a minus sign. So if I apply minus 1 over here, it will be minus cos minus n omega upon n square omega square plus, let's apply the upper limit. So if I apply the upper limit, it will be simply sin n omega upon n omega plus cos n omega divided by n square omega square minus lower limit. If I put a 0 over here, it will be 0 plus cos 0 upon n square omega square. So in the end we will get an expression like this, which we need to simplify further. Now we have calculated in the earlier stage omega, which is nothing but a pi. So wherever the omega is there, we will replace with a pi. So we will get an as, so I am removing this 0 and I know cos 0 is 1. So straight away it is minus 1 upon n square pi square. Sine minus theta is minus sine theta. So let's adjust all this minus. We'll get plus sine n pi upon n pi. Cos minus theta is cos theta only. So this will remain as it is, but because of this minus, it becomes plus. So you will get here plus cos n pi upon n square pi square plus sine n pi upon n pi plus cos n pi upon n square pi square, and in the end cos 0 is 1, so it is minus 1 upon n square pi square. Now we know sin n pi is 0 for any integer n, and cos n pi is nothing but minus 1 raised to n. So let's substitute over here so that this will become 0, this also becomes 0, and this becomes minus 1 raised to n, minus 1 raised to n. So let's simplify. So an will be minus 1 upon n square pi square plus minus 1 raised to n upon n square pi square plus minus 1 raised to n upon n square pi square minus 1 upon n square pi square. So if you closely observe, we will get this equal to an as 2 divided by n square pi square in bracket minus 1 raised to n minus 1. So here also, depending upon the value of n, we can have two values for an. Meaning, if n is even, minus 1 raised to that even number will be 1. So 1 minus 1 will always give you 0 for n even. But if n is odd, this minus 1 raised to that odd number will give you a minus 1. Minus 1 minus 1 will repeat. Minus 1 minus 1 will become minus 2. In the end, that will get multiplied with this 2 to get minus 4. So in the end, I can say an having two values, either 0 or minus 4 upon n square pi square. I will get n as 0 if n is even number, means 2, 4, 6, likewise. And I am getting this answer, which is minus 4 upon n square by pi square if n is odd. 1, 3, 5, like this. So this is the value of an. So Bn can be calculated like this: 1 upon half the time period. The x of t exists from minus 1 to 1 into sine n omega t dt. So we know time period is 2, so 2 by 2 is 1. So no need to write over here. So I can say Bn as, since x of t having two parts, minus 1 to 0, it is minus t, and 0 to 1, it is plus t. So if I solve this, let's change the limits and adjust this minus first. So I can make it 0 to minus 1, t sine n omega t dt plus 0 to 1 t sine n omega t dt. So u into v, this I will take as a u and this will become v. So if I use u into v, I will get, first, as it is, integration of sine is minus cos minus derivative of t is 1, and integration of this is minus will as it is and cos will become sine upon n square omega square, and the limits 0 to minus 1, plus same way over here, so t minus cos n omega t upon n omega minus 1 as a derivative, near minus sine n omega t upon n square omega square. Limits are from 0 to 1. So let's apply the limits to get a Bn. So Bn will get as minus 1 into minus cos minus n omega upon n omega. So what we have done, simply wherever t is there, I'll replace with a minus 1. This minus, first I will make it a plus, and after applying the limit, I will get sine minus n omega upon n square omega square. So this is just the upper limit of a first integral. Minus, let's apply the lower limits now. Now t is there, if I apply 0, straight away the first term will become 0, plus here I will get sine 0 upon n square omega square. Let's see for the second integral where the first limit is 1. So if I apply, I will get 1 into minus cos n omega upon n omega. Once again, minus minus will become plus, and limit sine n omega upon n square omega square. Minus, I need to apply the lower limit, which is 0. So if I apply the lower limit 0 over here, it will be same as this, 0 plus sine 0 upon n square omega square. Now we know omega is nothing but pi in our case, so Bn will become, here minus minus will become plus, and cos minus theta is cos theta only, and omega is pi, so I can straight away say it is a cos n pi upon n pi. Over here sine minus theta is minus sine theta, it's minus sine n pi upon n square pi square. Sine 0 is 0, so no need to consider. Over here once again minus will come out, and that become minus cos n pi upon n pi plus sine n pi upon n square pi square, because this term is 0. So now it's very simple expression. We'll get cos n pi upon n pi minus cos n pi upon n pi get cancelled. Sin n pi by n square pi square minus sin n pi by n square pi square get cancelled. So in the end, what I will get Bn as? Bn I will get equal to 0. So now all the three coefficients we obtained. A0 we obtained 1 by 2. An we are having two values. First we are having a 0, and second value we obtained as minus 4 upon n square pi square. 0 is for even number of n, and minus 4 upon n square pi square is for n is odd. And finally Bn will be having a value 0. So Fourier series representation of x of t can be written like this. X of t equals a0 plus summation n from 1 to infinity bracket an cos n omega t plus bn sin n omega t. If I substitute the values that we obtain, x of t equals 1 by 2 plus, now here we know this bn is becoming 0, so I can say this is n from 1 to infinity, and an value in general we obtain this. So if I substitute, I will get 2 upon n square pi square bracket minus 1 raised to n minus 1 into cos n, omega is pi, so n pi into t. So if we further implement the values of even and odd, I will get this equal to 1 by 2 minus 4 divided by pi square, in bracket it will be cos pi upon 1 square plus cos, here t will also be there, then cos 3 pi t upon 3 square plus cos 5 pi t upon 5 square. So it is only be present for odd numbers of n, and this will be the Fourier series expansion or a representation of x of t. Here is the end of a problem. Thank you.